Okay, good morning, ladies and gentlemen. Welcome to the 5th day of this summer course. I hope that you all still have full energy to study about coding theory and cryptography. My name is Khalida, and I am the Master of Ceremony for today. The first session for the next 3 hours is Coding in Secrecy. That will be delivered by Dr. Lin Fuchun from Nanyang Technological University. For Dr. Lin Fuchun, your lecture is ready to start. Time is yours.
Thank you. Okay, good morning, everyone. So I have like 3 hours, the whole morning. So please relax and follow me. I'm going to show you something really interesting and really simple. And I hope you can ask questions whenever you have any questions. Just stop me and ask. Otherwise, we have 3 hours, right? Okay. So talk is about a problem that is a simplified version of what we have in the paper with these 4 people. Some of them you may know, but maybe I should skip this slide. So it's really a very old problem. It started in 1975, maybe earlier. So let's see what it is. It is called wiretap channel, and you will see why it is called wiretap. So this is a normal model for coding. You want to send something from A to B, and you send it through a channel. And usually in coding, we consider error correction. The meaning is you want to remove the noise from the channel. Because noise are everywhere, we cannot avoid them. So we have to find out a way to remove them. This is the basic job in coding. But today we are going to consider a different task, which is called secrecy. So let's see. So these people in 1975, they consider an attacker. This attacker is wiretapping. Wiretapping is very obvious. He is not supposed to see the transmission, but he tried to see it. And he tried in the way of wiretapping. He used a wire, like in your phone at home. Some secret agent they secretly install the wiretap and wiretapping your communication. So this in 1975, Weiner considered this model, and he discovered if this wiretapper channel, if this one is noisy, that means the bad guy is seeing a noisier version of the communication. Then you actually can realize 2 goals. One is to remove the noise for the good people, for the receiver, and you can at the same time make sure that this guy does not have any information. That's 2 jobs: secrecy, to protect your privacy, and at the same time the basic one, the removing the noise one for the good guy. So today I will be focusing on the secrecy part, this part. Because this removing noise, this part is kind of is an independent topic, and I think in this workshop you will hear many people talk about it later. So now we look at a simplified version. Just a clear channel from the sender to receiver. Whatever the sender sends, the receiver can see it the same way. There's no noise in the channel. But we want to focus on this guy, and we want to make sure that our code can provide secrecy. I will explain what is secrecy. And this is called wiretap 2 channel. And I even remove all the complications about communication channel. I'm looking at a very simple way, very intuitive way of the wiretapper. Suppose the sender is going to send n component, block length n components, 1, 2, 3, 4, 5, n. And this adversary, this bad guy, can always see t out of n. So it's very simple, right? You cannot allow this guy to see everything. If he can see everything, he can see the same as the receiver. Then you cannot provide any secrecy. So you have to restrict. This t is smaller than n. So the sender is going to send n blocks, n components, and the adversary can see t out of the n. And this t component is arbitrary choice of the adversary. So the adversary, imagine you are the adversary, and you can pick whatever your choice of t. You just cannot go beyond t. At most t, you can pick t component to look. And I want to design a code to make sure that after you see t components, you see nothing. So this is a little bit interesting. Okay, so this is our the problem that we want to look at. And I told you that I will tell you what is secrecy. So how would you define secrecy? Okay, let's go for some intuition. So one way to define it is, so this bad guy, before he sees the T component, he might have some knowledge about the message that the sender is trying to send to the receiver. For example, the sender is going to send error bits message. He knows the length. He knows even more. If you are conducting a poll, voting A, B, C, D, then he knows that what you want to send is one of the letters from A to D. Before he attack, he has some knowledge about what you want to send. And then we look at after he sees T components. So after he sees T components, his knowledge remains the same. Is this okay for you? Is this definition of secrecy for you? Before you see the T component, you already know a little bit. After you see T components, you know exactly the same. Your knowledge did not increase. Okay? So this sounds like a reasonable definition, right? And the trick is, how do you make it mathematical? You cannot say this is an intuition, but you need to design the code. You need to prove that your code works. So we need to make a way to make it use mathematics to define it. Okay, so remember this is very intuitive. Just relax, and if you have any question, ask me. So when this is exactly equal, we call it perfect secrecy. This we will become clear later. Okay, now this is the mathematics that we need to make that idea into something rigorous. So, do you know entropy before? So entropy is something, if you see it for the first time, it's a little bit crazy, but this crazy idea works. It changed the world. Okay, this is a mathematical equation. You define something called entropy. And this x is a random variable over a set, this x. I'll give you an example immediately. Suppose you consider 2 to the n different objects. This calligraphy x is a set of 2 to the n anything. And you consider a distribution. A distribution is you assign probability to these 2 to the n objects. And the sum of the probability has to be 1. Okay? This is a distribution. You assign, so now you are in a set of 2 to the n objects. You assign probability for each of these objects. And the sum of the probability is 1. And then you have a distribution. Like what I show here. It looks quite small. I was expecting, I didn't expect that you were sitting so far. Sorry. So this is 2 to the n objects. Some objects are assigned 0 probability. That is why I have a blank here. Some points are assigned 0 probability. And the other points, 2 to the k of them, I assign them probability 2 to minus k. So indeed, when you sum them up, you get 1. I pick 2 to the k points out of 2 to the n points and assign them equal probability, 1 over 2 to the k. The sum is 1. This is a valid distribution. Okay, now I have a homework for you. What is the entropy of this distribution? I have a distribution, I have a definition of distribution, entropy here, and quickly computer tell me. I can help you a little bit. So this log is the log function that you know, you studied in your mathematics. So we know that log of 1 is 0. And when it's bigger than 1, log of x is bigger than 0. When x is smaller than 1, log of x is 0. It's negative. This is what we know about the log function. And since these probabilities are sum to 1, so each of them at most 1. So this log is going to be negative. This log is going to be negative. And you have a negative sign in the front to cancel out. It becomes positive. So did anyone figure out what's the entropy of that distribution? I will not go on until someone figure it out. That's a joke. Okay? Yeah, you only need the negative part, and you get a positive number. You can spend some more time trying to figure it out. So this entropy measures how much randomness that is contained in its K. Okay? So this mathematical equation magically characterizes how much randomness is in one distribution. For example, this one distribution with which is flat. We call it flat distribution. That all the probability are the same. Since this is minus negative k, you are going to get k bits information. This will become familiar to you after this talk, I'm sure. Okay, so now let's connect it to knowledge. So suppose you know nothing about this n bits string. That means you are uncertain about the value of n bits. That means you have a uniform distribution over 2 to the n. In that case, you are going to have you're going to use this equation and find out you have n bits entropy, which means n bit uncertainty. And assume that I tell you some information about the n bit string. I tell you t bits out of the n, for example. And now you can restrict the possibilities to a smaller set. Okay? If it doesn't, if it is not consistent with what I tell you, then you can remove them. And what's remaining will become with a higher probability. So after I tell you some information, your distribution of the 2 to the n bits becomes k bits, becomes this one. In this sense, I can say that what I told you contain n minus k bits in knowledge. And after I give you the n minus k bits knowledge, your uncertainty decrease from n bits to k bits. It will work this way, and magically it does. So your entropy about secrecy coding is uniform. After this talk, after I give you some information, your knowledge about secrecy coding will decrease. The entropy will decrease. Let's see how many bits decrease. I think there is a game that you are only allowed to ask several questions, and each time you ask a question in a yes or no style. And after n questions, you can narrow down to the question. So each time you get 1 bit information. Each time you get 1 bit. After n bits, you get all the information. So this is actually the entropy idea. Okay, let's get back with this powerful mathematical tool called entropy. We can go back and define secrecy. Historically, like in 1975, Weiner considered a very, very weak secrecy in this sense. So he first assumed that the message is unknown. The adversary does not know anything about the message that Alice wants to send. So that is error bits uncertainty. And he wants to make sure that he has a code, he can design the code, that after the adversary sees T components, his information about the secrets will decrease a little bit, but not too much. This small o of error means an amount that may be growing with error, but is growing much slower than error. So small o of error divided by error will tend to 0. This is not very good actually. After you compare with other secrecy definitions, you will know. So that some people say this is too weak. I can consider a stronger secrecy. So I allow some decreasing of uncertainty, but this amount has to be very small. It's becoming smaller and smaller as error grows. But then later, people get smarter and smarter, right? People quickly say, especially when the cryptography people, they look at this definition and say this is unacceptable. You allow some small number of bits to be known to the adversary, but in cryptography they consider not even 1 bit. Not even 1 bit. I don't want to lose anything. Sometimes losing 1 bit is already terrible. So in cryptography, they are not happy with these definitions. Let's see what's this cryptography definition of secrecy. And before that, we need some mathematics again. So if you know this before, please be patient. I know this part could be very dry. Yeah, so I brought water. Okay, so this is the definition of statistical distance. It is also called the total variance. And I will walk you through using an example. So, these distributions again. This time we are not looking at one distribution. We are looking at 2 distributions. So, we are looking, now I have 2 distributions exactly the same. Just the one that I showed you previously, k-bits uncertainty. And if you use this definition, you can see that this probability minus this probability, since they are the same, so the difference is 0. And you are summing a lot of 0 and divided by 2. It gives you 0. So we know that this SD distance, statistical distance, when you have 2 distributions identical, then it's going to be 0. This is the same as the distance we have for everything. Okay? And let's see how big you can get. What is the biggest that you can get? So imagine I do a little bit of change. I define a new distribution, this one x prime, which is different from x. And it is different if you look at this part carefully. So while I had 0 probabilities, now I have 2 to the minus k. And while I had 2 to the minus k, I have 0 now. Now someone quickly tell me what's the statistical distance of these 2 distributions. Every point they are different. Every point they are different by 2 to the minus k. So you altogether okay. Hope you are not too tired. The answer is 1. And you can actually find out a few other examples. And you can see that the biggest the distance can get is 1. So the smallest is 0. It's always non-negative because you have absolute value. And the biggest is 1. The furthest, the biggest distance is 1. The smallest is 0. It's always non-negative. And we will need this to compare how close are 2 distributions. Back to the definition of secrecy. So now we can use it here and define what is called semantic security. You don't need to care about the name. This is the name they call it in cryptography. The idea is as I said, you are not allowed to lose even one bit secrecy, uncertainty. So even at the beginning, the adversary already know a lot about this message. What he is not certain is whether it is message 1 or message 2. Only 2 choices, only one question, yes or no. And after he observes T components, still it is difficult for him to distinguish which one is the sent one. So this is much stronger than the previous one we saw, right? Not even one bit. And difficult to distinguish is characterized by statistical distance. So now we are going to encode our message, and the encoding algorithm or the encoder contains some randomness. And after you add some randomness into the message, it becomes a distribution. When you look at only T components of the code words, you get a partial distribution. You get the distribution, you get the distribution for the T components. And I want to make sure that even you are given, even the adversary know that we only have 2 messages, message 1, message 2. After he sees T components, he still does not, he still cannot make sure which one is the sent one. So we say, after he look at any choice of T out of N, he cannot distinguish S0 and S1, the code word for S0 and S1. Okay, I haven't had any questions so far. Maybe it's a good time to see if anyone would like to ask a question or comment. Yeah, or you have a little bit of discussion with the friends sitting next to you. So I describe these definitions of secrecy, and at the end, we are going to only look at perfect secrecy and semantic security. These two are related in this way. As we have seen, when this distance is 0, they become identical. So that brings us back to the perfect secrecy. So for perfect secrecy, it doesn't matter how many bits of message you are sending, how many bits uncertainty at the beginning, because there's no change of entropy. So starting with 1,000 bits and starting with 1 bit is the same for perfect secrecy. So our new result is going to be on semantic security, which is the second half of this talk. And for the first half, let's do some warm-up using the perfect secrecy. This warm-up part is more mathematical, and I am sure all of you will be very familiar with the tools that is used. Because I asked your teachers and your colleagues, can I assume anyone in this room are familiar with linear algebra? And he told me yes, absolutely. So that will be very intense, linear algebra. Other than that, I explain every single definition together with exercises. So after this point, there's going to be no exercise, just the game, just the interesting part. Okay, so we define our goal. We want to design code for secrecy. And I told you what is secrecy. the definition. Okay. Now, in order to use it, we visualize the definition using this example. This is more like a combinatorics way of looking at it. So surprisingly, the code book is a partition. So the code book is not a subset of the n-dimension space, but the whole space, all the 2 to the n vectors. And what is interesting is only in how I partition this code book, these 2 to the n vectors. So be very careful. The design is only in the partition, not about the choice of the vectors. I have all the vectors. I just divide them into okay. There is supposed to be difference in color. So the upper half was yellow in my computer, and the lower half was green in my computer. Sorry. And next time I should use some other color. So the idea is one message is corresponding to many code words. For example, the yellow, imagine this is yellow. In this yellow code words. And this green one is corresponding to these green code words. And there could be more messages. But since we are considering semantic security, only 2 messages can define it, okay? So how is the code work? I am going to choose one vector in this set randomly. I just flip some coins and I pick one randomly from the set of code words corresponding to the message. For example, I have 8 code words corresponding to all 0 messages. Then the probability of the code word for all 0 is, this guy is 1/8. It's very clear, right? Same as other code words. They could all be chosen, have been chosen with the same probability. And in my definition, I told you I want to allow the adversary to pick T out of N. For example, T is 2 and N is 7 here. So this adversary arbitrarily pick 2. For example, this column, the second and the fourth. And what is he going to see? It's uncertain, right? It is probabilistic, right? Because the code words is probabilistic. And what he sees is probabilistic too, right? So for example, he's going to see 2 zeros if the code word is this guy. He is going to see 2 zeros as well if the code word is this guy. So his probability of seeing 2 zeros is 1/4. And if you keep going, his probability of seeing 0, 1 is also 1/4. 1, 0 is also 1/4. 1, 1 is also 1/4. Because I play some magic. I define my partition in such a way that every 2 bits will appear with 1/4. I'll tell you why, and you can do it and show it to your brothers or your cousins. Okay. What's the distribution of the 2 bits for the message or 0? It's a uniform distribution. 1/4 for 0, 0, 1/4 for 0, 1, 1/4 for 1, 0, 1/4 for 1, 1. And I will tell you how I generate subset of code. I just add this vector to every one here. And you can see that this subset will have almost the same property as this one. So you will have the same 1/4, 1/4, 1/4, 1/4 distribution. Same for each message. You repeat this for every message. And you can see that the distribution of the two components is uniform for every message. So the distribution here for any choice of 2 out of 7, and the distribution for message S1 for any choice of 2 out of 7, they are the same. They are smaller than epsilon, a very small constant. They are, in this case particularly, is 0. So this is what we should have in mind all through this talk. Our goal is to design a distribution that satisfies this kind of property. And I will show you how I design it very quickly after this one. Okay, this is not the one. We can, if you already know many similar topics, then you will find this useful. Otherwise, you can just relax and give me 2 minutes. So we consider perfect secrecy and semantic security. These are the two these are two acceptable definitions of secrecy in cryptography. And this secrecy code that we are designing is related to something in cryptography that is called all or nothing transform, short for AONT. It doesn't matter. It's only some introduction. And it is also related to secret sharing scheme, which is more important, that you are going to have my friends, Roma, giving talks on secret sharing next week. So it is related to secret sharing. And I'll quickly tell you what is secret sharing scheme. I believe many of you have heard about it because it's very, very classical. So you have a secret, the one that just disappeared, that you want to split it into 12 parts. And you want to make sure these 12 parts satisfy 2 conditions. If you have enough people to come together and pool their shelves, you should be able to recover the secret. Or you can define how many is enough. In this case, it's like how many? 9. 7. Yeah, I'm not good at mathematics. So you can define, you can actually pick any number between 2 and 12. This is enough number of people, you can recover the secret. And if this guy, number 10, didn't come here, if you don't have enough people, you have absolutely no information. This is secret sharing. It's very similar to what we have seen in the first slide. So people always say wiretap channel and secret sharing are the same thing. I will tell you the difference. Okay. So yeah, let's compare them. So we can consider, instead of clear channel, you can consider the adversary can at the same time actively delete some components. For example, R component remaining, and then it becomes secret sharing, the discretion of problem. R components can recover the message, and T has no information. But I told you I'm going to tell you the difference They are totally different objects. Otherwise, we cannot, we are mathematicians, we are researchers, we cannot give them the different names for the same people, for the same objects. So the major difference, number one, is in coding we consider a fixed alphabet, like binary, or even Q array. This is the coding style. Also, coding, we do not mind the block length. The block length usually goes to infinity to achieve better performance. Usually when we design code, because we are not, well, we are not genius, we are human. We cannot get what we want to get. So we say, okay, if you allow n to go to infinity, then you can have what we promise. This is coding style. In secret selling, you have 12 people. Like you want to divide, like once I have a friend, he and his girlfriend decided to share their bank account, the money in the bank account. So the 6-digit password, the guy keeps 3 and the girl keeps the other 3. So this is sharing the secret between the two. You don't allow the n to go to infinity. You don't want the n to, you don't want to share, there's no motivation for that. So, again, difference, we go to infinity. While in secret sharing, n is usually quite small, fixed number. And as in coding, the efficiency is measured by coding rate. The message length divided by the code word length. You want to minimize the cost. So this is the 3 differences. And in particular, in this simple problem, that is the theme of this talk, the capacity is 1 minus tau. Tau is T over N, the fraction. This is our goal, and we did achieve it in the second half. Okay, we finally arrived at the constructions. This is supposed to be a warm-up. Okay, how did I generate the magic partition? Here is how I generated it. I use a matrix, a square matrix. Okay, you can see how I do it. For this message, for example, 4 bits, I use 3 bits of randomness. 3 bits is 2 to the 3 is 8. They will give me 8 code words. If I multiplied this vector by this square matrix, 7 by 7. Okay. And what I require for this matrix is any T columns are linearly independent. I mean only this part, only this lower part. I don't really care what is here, as long as the 2 parts together give me a invertible matrix. They are, all the rows are the number of rows here. Your matrix is not as good as the Mendeleev matrix. Okay, well, the biggest problem is that we didn't achieve our goal. There is still another bound. Q has to be bigger than a quantity determined by this thing. And when we say we want to have a code for any wiretap 2 channel, we want to have a code for any tau, any fraction. But if your Q is by a constant determined by tau, if your tau is very big, 1 minus tau is very small, then your Q is also very big. It is not a constant. It depends on tau. And our goal is Q is a constant independent of n and tau. Try something else. Random matrix. You pick a binary matrix uniformly at random, 0, 1 with equal probability for every single entry. With high probability, you can get a very good matrix for generating the distribution that we want, the magic distribution. But there's a catch. With high probability. But how can you trust it? Every time you generate such a matrix, you need to test it. And it takes well, you cannot test it. You can only believe that it is almost good. So this is not really an explicit construction. It is something like the coding problem. When they started with uniformly use a code, then it is the best code. But we have been spending so many years trying to find a code, which is recently closed by the polar codes. Okay, so what's the good thing about this? You can make it a binary, really independent of the everything. And there are problems. It is not explicit because it is uniformly at random. You just keep flipping coins, And can you believe it? You keep flipping coins and you get the best. Not the best, or the very good one. And not very good in here, it only works when tau is smaller than 1/2. This is also related to the entropy function. Binary, when h of 1/2 is 1, then you cannot go. And very bad rate in that t has to be much smaller than previously. It's only very small. The one I show you is something like this one, binary, right? You remember, you know that the t, I can only go to 2. I cannot even go to 3. So these are the 3 things. Yeah, bad news still. So all these 3 constructions, we use matrices. We use linear space, and they are perfect. They give you perfect secrecy. And there's a bound without looking at any construction. If you assume perfect secrecy, then your Q has to be bigger than this quantity. So we can turn this bad news into a good news. We don't need to try anymore because it's impossible if we try this way. Okay, that's the end of my first part. So how many minutes do I have left for the first part? Oh, 34 minutes for the first part. So questions? Good time, yeah. You can ask me to go back to which part that you find interesting. Before you ask any question, I do some recap, which is supposed to be the beginning of next talk, but I can use this slide. So I tell you what is perfect secrecy and what is semantic security. These two are the only two things that we cared about in this talk. And I show you three constructions. They all have their problems. And some of them are very old. I think all of them are very old, even older than me. And what I'm going to show in the next half is we have optimal construction that achieve what we want to achieve. Okay? So let me go back, and if you have any question, please. I can even go back to the first slide and use the 30 minutes to give the talk again. Okay. Yeah, maybe we go back to the exercises. I don't know how to do this. I have some more exercises for you. If you don't want to ask questions, you can take out a piece of paper and find out what's the statistical distance between these two distributions. I didn't bring any gift. Otherwise, anyone answer the correct answer, I should give an apple. So these are 2 to the L different objects. I have a uniform distribution on the left. Uniform. Each point occurs with probability 2 to minus L. This is uniform. This right-hand side is also 2 to the N objects, but half of them have probability 0. Half of them have probability 0. So it should be clear by now. Try to find the distance. And after you find it, go on and say the right-hand side is only 1/4. The rest are 0. Only 1/4. Here is 1/2. The other half is probability 0. And if you consider only 1/4 non-zero and the rest are 0, what's the distance? And if you are not satisfied, you can go 1/8, 1/16, and etc. It's just for fun. And I want you to ask me questions. That's much better. We make good use of the time. So if there's no question, can I suggest that we begin the break now? And whoever needs to go out for food or for everything can just go ahead. And whoever would like to ask me question can stay, and I will hang out with you. Okay? So,
I'm really sorry. I arrived late. In fact, the last slide you're talking about convertible matrix. So the goal is to construct some convertible matrix, right?
yeah, the invertible. So the goal is to construct n by n invertible matrix with the special structure in the lower half. Lower half.
And then as you say that the good candidate may be some generator matrix of algebraic geometrical, right?
Yes. Yes.
So the first case may be algebraic geometrical genus 0 is a Ritz-Salmon code.
Yeah, it's with Salmon code.
Matrix look like.
Yeah, the minimum. Yeah.
But for Ritz-Salmon code, when the length go to infinity, it's like.
Yeah, Q is too big.
So you said that you get some optimal from algebraic geometry.
Near optimal.
No, it's not.
Near optimal.
Very optimal.
Near optimal.
It's from algebraic geometry code, right?
Yes. From bigger, actually bigger. They have a tower of fields that can Q to be a constant, and still this one goes to infinity.
So for the matrix you are looking for, is it only